roughly 311 miles, about 500 kilometers west of Oregon's shoreline, far below the gray swells of the Pacific. A hidden volcano rises from the abyssal plain. This undersea mountain, called Axial Seamount, sits squarely along the fiery backbone of the Pacific Ring of Fire, the vast horseshoe of faults and volcanoes that girdles the ocean. The Pacific Northwest is no stranger to restless geology. It is home to the Cascades and to infamous peaks like Mount St. Helens, whose 1980 blast still serves as a cautionary tale. The story stretches back millions of years to when the Pacific Plate began diving beneath North America. That slow-motion collision helped build the Cascade Arc from Northern California into British Columbia, and it also set the stage for submarine giants like Axial. From the seafloor, it climbs like a dark cathedral, its summit still roughly 5,249 feet, about 1,600 meters, beneath the sea surface. Lately, something unusual has been stirring down there. In a single day, instruments recorded more than 300 earthquakes around Axial, a spasm of motion that is far from routine. The pattern of shaking has scientists on high alert because it resembles the run-up to the seamount's previous eruptive episodes. One veteran oceanographer put the risk in stark terms. If this were happening beneath a town rather than beneath thousands of feet of water, emergency managers would already be clearing neighborhoods and putting evacuation plans into motion. The Pacific may look calm from a ferry deck. The forces below are anything but. So what's driving this drumbeat of quakes? The best explanation points to magma creeping upward through fractures in the oceanic crust. As molten rock pushes into the plumbing system beneath the summit, it pressurizes the volcanic edifice. Think of a balloon being slowly inflated inside a rigid box. At some point, the pressure has to find release. When that moment comes, the seafloor can split, lava can pour out, and the volcano can undergo an eruption, measured not in towering ash plumes, but in rivers of basalt that harden into black glass on contact with cold seawater. The year 2025 has already delivered several eyebrow-raising bursts of activity. In June, instruments tallied an astonishing flurry, more than 2,000 earthquakes in just 24 hours. That spike eventually eased, settling back to roughly 100 tremors per day for a time, but counts have again climbed into the hundreds. Even without any one massive jolt, the sheer persistence of these tiny quakes is a red flag. To grasp the scale, remember what happened the last time Axial really let loose. During the April 2015 event, over 8,000 earthquakes were logged in a single day. That is the tempo of a volcano in full swing. Today's numbers are lower, but the trend line and the style of the signals echo that run-up. And that is why researchers are treating the present sequence as more than a curiosity. A second, equally troubling clue is showing up in the shape of the volcano itself. Axial appears to be inflating, its surface subtly lifting as new magma collects in a reservoir beneath the summit. Before the 2015 eruption, that ballooning reached a notable threshold, and measurements now suggest the edifice has swelled back to similar levels. The tempo of uplift has accelerated too. Whereas typical years saw the ground rise on the order of 2 to 4 inches, roughly 5 to 10 centimeters, the rate jumped dramatically beginning in January 2024. By July, some stations near the center of the caldera had captured as much as 6 inches, about 15 centimeters, of cumulative uplift, and peak pockets were pushing toward 10 inches, around 25 centimeters. That's a remarkable amount of motion for rock to undergo in such a short interval, and it fits uncomfortably well with the surge in microquakes. Both are classic symptoms of a magmatic system under pressure. All of this is unfolding inside a volcano with serious dimensions. Axial is not a neat cone. It's a sprawling complex capped by a caldera and rift zones that stretch for miles along the seafloor. The main magma storage zone sits around 2,625 feet, about 800 meters, beneath the top of the edifice, a sizable chamber of molten rock feeding the system. Although its summit remains more than 1,000 meters below the ocean's surface, which muffles direct effects on coastal communities, there is nothing small about the forces at work. For volcanologists, Axial is both a laboratory and a test. Here's a system we can watch closely, one that erupts often enough to study modern processes in real time, and one that can teach us about the rhythms of more dangerous volcanoes on land. Predicting eruptions is notoriously difficult, but Axial may be giving scientists the best shot yet at a well-timed forecast. The volcano has a quirky personality. Periods of rapid inflation can be followed by quiet plateaus, then by renewed surges. But the current combination of inflation, seismicity, and the sheer pace of change has led some researchers to a striking conclusion. Odds favor an eruption before the end of 2025, possibly at any time. That doesn't mean a cataclysm is guaranteed, and the ocean will absorb much of the spectacle. Yet from a scientific standpoint, capturing such an event with modern eyes could be historic. That's because the monitoring toolkit on site is far better now than in previous cycles. A sophisticated network of cables, junction boxes, and sensors sits on and around the caldera, streaming data continuously. Tilt meters watch the ground breathe. Pressure gauges register tiny changes in the overlying water column. Seismometers listen for the crackle of moving magma and the pop of breaking rock. Some nodes are tied into cameras and chemical sensors, ready to catch visual signs, plumes of shimmering water, sudden turbidity, or hydrothermal fluid bursts, should the seafloor split. Instead of occasional research cruises, stitching together snapshots weeks or months apart, scientists now have a live feed from the deep, second by second. If Axial opens a new fissure, that system could record the sequence with a level of detail never achieved for a submarine eruption. The earthquakes being tallied are not large in the way the public imagines earthquakes. Most cluster around magnitude 1 to 2. But in a volcanic setting, that's exactly what you'd expect. Swarms of small events that collectively map the path of magma as it wedges itself into cracks. Each tiny quake is a stress whisper, a brittle fracture here, a slip there, a local pressure drop, followed by renewed push. The pattern matters more than any single number. A broadening swarm, increasing rates, a change in the dominant depths. These are the signatures forecasters watch, and recently those signatures have been trending in the direction of unrest. It's worth emphasizing that undersea eruptions differ profoundly from those on land. There will be no ash cloud blotting out the sun, no red fountain visible from coastal highways. The pressure of 1,000 meters of seawater forces lava to quench instantly into jagged pillow shapes, piling up like toothpaste squeezed into ice water. Still, the consequences can be significant. New lava can dam or reroute hydrothermal circulation, altering ecosystems. Seafloor topography can change over days. In some cases, gas release or rapid heating can drive local hazards at the surface, though at Axial's depth, the ocean generally dampens such effects. For ships and nearby infrastructure, the main risks would be to sub-sea floor cables and instruments, not to ports and cities. Even so, studying Axial is not an academic luxury. The physics of magma moving through rock are universal. Lessons learned here, inflation thresholds, the relationship between seismic swarms and dike intrusions, the way pressure migrates through a branching rift network, translate to stratovolcanoes that do loom over towns and highways. Every data point from Axial sharpens our playbook for hazards on land. If researchers can validate a reliable chain of precursors at this seamount and peg the timing of an eruption within a meaningful window, it would represent a milestone for eruption forecasting writ large. None of this erases the reality that volcanoes can faint. Axial's history includes stretches of rapid uplift that stall, intervals where quakes scatter then regroup, and episodes where magma intrudes along a rift without breaking the surface. Forecasts must dance with uncertainty, but uncertainty is not ignorance, and it is not paralysis. It is a quantified range, narrowed by each new sensor, each fresh data set, each additional hour of continuous monitoring. Right now, the picture looks like this. The volcano has reinflated to levels comparable to those seen before the 2015 eruption. The rate of inflation accelerated markedly, beginning in early 2024. Earthquake counts surged to extraordinary highs in June 2025 and continue at elevated levels measured in the hundreds per day, and the overall behavior suggests a pressurized system. The simplest interpretation is that magma is on the move and that the system is trending toward a release. If and when that release happens, the sequence is likely to unfold rapidly. A dike, a blade-like body of magma, could propagate along one of Axial's rift zones, opening a fissure on the seafloor. Seismicity would spike, then reorganize into a migrating front as the intrusion advances. Tilt meters might register sudden steps. Pressure sensors could show subtle changes as warm fluids pulse outward. Cameras, if lucky enough to be pointed in the right direction, might catch the water clouding and shimmering. Lava would extrude and cool into lobate pillows, building new crusts, even as the underlying reservoir deflates and the ground above sags. After days to weeks, the system would quiet, leaving behind a freshly minted patch of ocean floor and a trove of measurements for scientists to decode. For now, the best course is vigilance. The deep ocean network continues to hum, logging every tremor, every millimeter of rise or fall. Research vessels stand ready to sail when weather windows open. To ground truth, the signals with plume sampling and high-resolution mapping. And the public, though insulated by distance and depth, can take real comfort in the fact that this is a volcano we can watch in detail, one whose behavior is teaching us how to read the signs at other, more immediately consequential volcanoes around the world. Curiosity about Earth's hidden machinery is more than a hobby. It's a form of preparedness. The more we understand how magma moves, how rock responds, and how seafloor systems breathe, the better we can anticipate the next chapter, underwater at Axial, or atop a mountain closer to home. If this kind of deep time detective work fascinates you, stay tuned. We'll keep translating the pulses of the planet into stories you can see and understand, as this undersea giant writes its next line in the Pacific's long volcanic script. A startling development has shaken modern volcanology. Far out in the Japanese archipelago, on a lonely Pacific outpost named Uima, a sudden and dramatic event has reminded scientists that this island has never truly slept. Uima lies well south of Tokyo, about 777 miles away, often recorded in older local notes as roughly 200 to 250 kilometers, and appears on charts as a sharp triangle laid upon open sea. On paper, it is small, about 5 miles, 8 kilometers, from tip to tip, and roughly 2.8 miles, 4.5 kilometers, across at its broadest point, a speck with an outsized story. Uima's Japanese name points directly to its chemistry. Sulfur Island, the label fits. The ground sits atop the rim of a flooded caldera, roughly 5.6 miles, 9 kilometers, across. The unseen engine that has been lifting the land year after year. For centuries, the island has been rising, not in a single jolt, but as a stubborn, measurable creep. Modern measurements put the average rate near 10 inches per year, about 25 centimeters. You can read that uplift in the rock itself. Wave-cut ledges carved in the 17th century now perch around 131 feet, 40 meters, above today's sea level. The island's most famous image is human, rather than geologic. The photograph of American servicemen raising a flag on the island's highest ridge, about 525 feet, 160 meters above the sea surface. That monument to effort and cost rests on volcanic scaffolding, piles of lava, ash, and broken rock that have been stacked, baked, and then lifted by a crust that refuses to stay still. The historic picture can distract from the restless background, whispering fumaroles, incrustations of elemental sulfur, and the faint, constant hiss of gas searching for daylight. On September 1st at 7:14 p.m. local time, the background became the main event. A sharp explosion opened new ground along the coast and turned a quiet shoreline into a theater of motion. Japanese researchers gave the fresh vent a name, Shidarama, and began documenting a scene that looked almost staged. A hole torn through coastal rock, a storm of fragments lofted and flung, and a plume climbing into the evening air. Dust-fine ash mixed with pebble-sized lapilli, orange with heat. Half-molten bombs arced upward and fell with heavy, perilous grace. The sound carried far over the waves. a rolling report that announced a system finding a new way to breathe. Local observers reported minor collapses along the new lava ledge, consistent with rapid erosion. What gave the blast its punch was the colliding chemistry of heat and water. Magma, well above 1,800 degrees Fahrenheit, 1,000 degrees Celsius, met cool Pacific seawater. The result was a sudden phase change. Liquid water flashed to steam on contact, expanding violently and amplifying the energy already stored in the melt. Volcanologists call such events phreatomagmatic, a word that can be unpacked to something like this. Magma plus water plus confinement equals shattering pressure. For minutes at a time, the shoreline behaved like a pressure vessel with a failing lid. Almost immediately, the sea began to carry away a second signal, pumice. Frothy, gas-rich melt, shattered and quenched into tan, bread-light rock full of sealed bubbles. Because it is so porous, pumice floats. It rides the ocean like rafts of cork. Whitish patches spread from the vent, then merged into drifting carpets that stretched in wavy sheets across the swells. Mariners learned to treat these belts with care. Pumice can clog cooling lines, abrade hulls, and hide hazards just below the surface. Overhead, the plume drew a layered sketch of the eruption's internals. Chalky white columns signaled steam, the water component. Gray curtains and darker bands betrayed suspended ash, the rock component. Watching that palette change in real time helps field teams judge the balance between water-driven fragmentation and direct magmatic discharge, especially when instrumentation is sparse at the coast. The outburst did not arrive without warning. In the weeks beforehand, island seismographs recorded strings of microquakes, too small for most people to feel, but unmistakable in the data. High-precision GPS and satellite radar showed the ground flexing by millimeters, numbers tiny in isolation, but loud in context. Deformation is the language of pressure. It is how a deep reservoir clears its throat. Fumaroles intensified. Their vapors, especially sulfur dioxide, the gas that smells of rotten eggs, rose in thicker streams. Gas tends to get out before magma does, so these plumes act like letters mailed from the subsurface, arriving days or hours ahead of larger news. A kitchen analogy helps. Take a sealed bottle of soda. Under pressure, the carbon dioxide stays dissolved. Release the cap and bubbles race upward, opening channels and pockets that were invisible a moment before. In many ways, magma behaves similarly. As pressure falls in parts of the system, dissolved volatiles unmix and seek escape. They pry open cracks, knit fractures into conduits, and can redirect the flow entirely. Uema's magma, rich in alkaline components, with tracheandicytic to trachytic tendencies, has the viscosity to trap gas and build pressure. That makes for eruptions that are especially explosive when water is involved. The caldera below Uema complicates everything. Instead of a single pipe beneath a single summit, the subsurface resembles a tangle of dikes and sills, side streets, rather than a highway. Existing vents do not own exclusive rights to eruption. Magma can thread an unmarked path, meet seawater at the edge, and construct a brand new opening. Shaidarama appears to be exactly that, a shortcut to the surface that did not exist a day earlier, situated where fractured shoreline rock and hungry melt could meet. Is Shaidarama the start of a longer sequence? It may be. New vents sometimes open in clusters, or one vent may wax and wane as supply shifts within the reservoir. The hazards in this coastal setting are blunt. Littoral systems can pivot from calm to life-threatening without generous lead time. Steam-driven jets can hurl dense blocks. Ash can blind navigators and choke engines. Pumice fields can mask collapsing benches and snag propellers, and the chemistry matters for people downwind. Sulfur-rich plumes can irritate eyes and lungs many miles away if the breeze carries them shoreward. Japan treats Uema and its cousins with patient attention rather than panic. Networks of seismometers, cameras, gas sensors, and GPS benchmarks feed into national watch rooms where shifts are mapped against experience. The goal is not to stop an eruption. No one can, but to understand it quickly enough to keep people and aircraft out of harm's way. When the coastline is the volcano's lip, notices to mariners must be nimble. Evacuation guidance must be clear, and pilots must have real-time plume advice before wheels leave the runway. The question of uplift returns again and again. Why does the island climb at all? Beneath Uema sits a reservoir that behaves like an inflating bladder. As fresh melt and gas arrive, the crust arches. Over decades, that subtle dome adds up to dozens of feet. Storms and waves record the change unintentionally. Sea caves that once met the tide now sit high and dry. Even the historic battlefield's contours owe something to this persistent breathing from below. Slow motion and sudden drama occupy the same address on Uima. Water, the island's constant neighbor, is also its impatient partner. It chills lava into glassy shards and flashes to steam with almost explosive eagerness. In many eruptions, the sea is a receiver of debris. Here, water is an active ingredient that pushes events into a different regime of violence. The spectacle can be breathtaking. Pillars of white and gray rising into evening light, glitter falling like snow in the plume's wake. But beauty is a poor safety signal. Distance and timing, not photographs. Keep people safe. This is not a call to alarm so much as a reminder about scale and tempo. The system that lifted 17th century shoreline markers 131 feet above today's waves is the same one that, on a September evening, opened a new vent where no map showed one, and lofted incandescent stones skyward. The past and the present share plumbing. For crews stationed nearby, for researchers, and for ships passing just offshore, the practical rule holds. Stay informed, keep clear when signals stack, and give the island room when it announces itself. Volcanoes teach in hard ways. Uima's latest lessons were plain. Microquakes are whispers. Deformation is a posted notice. Gas is a message from the deep, and the plume's colors are chalk on a blackboard. When those notes arrive together, shorelines can change in an afternoon. Today, the new name on the chart is Shidorama. Tomorrow, another may appear. In the end, Uima's September burst is more than a line in a field report. It is a living demonstration of how Earth's interior sends signals to the surface through pressure, heat, water, and fractured rock. Here, fire and sea share a boundary and sometimes collide. Respecting that rhythm is not superstition. It is literacy in a place built by forces that move whether or not anyone is watching.